Welcome, ladies and gentlemen, and thank you for your time and giving up your evening. I really just wanted to talk initially about, how I've structured this, and I do apologise if towards the end this does become a little self-indulgent, because I pulled out some of the very early projects I worked on in GPS and just wanted to talk a little bit about those, because I think they provide a sort of a context for how much of the innovation in GPS actually happened in the early days. And I also want to apologize to any professors in the room or in the virtual room. Of course, we shouldn't really refer to Einstein as Mr. Einstein. We should refer to him quite correctly with his full titles. But actually, when he did his early work on general and special relativity, he wasn't actually a professor. And I think that's indicative sometimes of, how technology and innovation happens. It happens sometimes in the oddest places. It can be in a patent clerk's office. It can be in, in the military. It can be in small technology accelerators in the US or in the UK or wherever in the world. So I'd like to talk a little bit about GPS, GNSS, its early days. Talk a little bit about some of the new innovations and how the history of GPS has influenced some of the current decisions we're taking around choices around using new technologies, whether it's Galileo, whether it's OneWeb, whether it's some of the new innovations that are happening. These stories have a long history and a long thread. And one thing about storytelling and narratives is that they're often built up over many years. And GPS is very much a technology that's been built up over many years. In fact, effectively the full period of the space race. So let's move on. Let's just do a little bit of an update of where we are today in the current satellite navigation system landscape. And I'm going to bounce around between using the word GPS, sat-nav, GNSS, and really by that I mean the ability to use space-based technology to navigate a position on the ground or on the surface of the Earth. Now, at the moment, we actually have 3 fully functional global satellite-based navigation systems, global navigation satellite systems, operating around the world. 2 are in what's called full operational constellation or full operational service. Galileo, we're still trying to debate whether it's formally announced that it's FOC. Originally, it was planned to be FOC in 2020. All the satellites are up there. They're all the latest generation, but actually I'm not sure they formally announced it. And if I've missed that, I do apologize. So we have 3 global systems, and then we also have 4 regional systems, which are there to augment or improve the performance of GPS or GNSS in a local area, or are to provide a degree of independence to some of the countries and who want to use GPS either for military or civilian applications. If we look very quickly, and I'm not going to talk too much about the technology behind GPS in the sense of its fundamental structure. I'm going to talk more about the application space, but initially let's talk about some of the basic sort of parameters. We have GPS, the Global Positioning System, Navstar. Currently, I think last check I made, 31 satellites in 6 middle Earth orbits, owned and operated by the Department of Defense. We have a very parallel development called GLONASS, owned and operated by the Russian Ministry of Defense. That's had a problematic history, but now is stabilized, and there's currently 24 satellites in 3 middle Earth orbits. And then we have Galileo, owned and operated by the European Union, ESA, and the operator is essentially a consortium of technology organizations across Europe. And there we have 24 satellites in 3 planes. So altogether, that's an awful lot of space hardware. And in fact, if we take the augmentation systems, I think at the last count, we had over 108 platforms in space providing ranging signals and some other services. In fact, GPS has a number of services. It has originally had some atomic flash detection capability. Galileo has some SAR, some search and rescue capability. And so whilst these satellite systems are primarily used for navigation and surveying, they also have some additional capabilities tucked away in the corners. I'd like to talk a little bit about a timeline, and I hope you can see this timeline, because I think this helps us frame the importance of space to obviously navigation, but more importantly, it gives us a context of how much was achieved in the very early days of navigation satellites. And of course, it all starts with Sputnik, the launch of Sputnik in 1957. It was only a matter of a few days after Sputnik was launched that scientists started to work out that you could actually determine ranging or measurement information from the Doppler shift coming from the frequencies transmitted by the Sputnik satellite. And that actually became very quickly a requirement and a capability that the US wanted to build and develop. And literally within around about 7 or 8 years, they had built and launched and declared operational the first satellite navigation system, actually called NavSat. It's a transit, a Doppler-based system. Provisionally, there was meant to be 6 satellites up there, but in fact, there was more than that. There were spares, and there was first and second generation satellites. But that first gave us the taste of using navigation equipment based in space. And I think what's quite fascinating there is the speed of that process from 1957 to 1964. And behind that, you must imagine how fast the development, how much money was poured into this. And of course, it was being driven at that point by a military customer. And the customer, the primary customer for NavSat was actually the ballistic missile submarines. It was the nuclear submarines that required accurate navigation to calibrate their very expensive but very clunky inertial navigation systems. And so the first transit sat-nav systems were really used to allow a submarine to pop up, get a fix. It took a little while to get a fix. It was accurate to about 100, 150 meters, but that was good enough to allow them to essentially reset their very expensive inertial navigation systems and pop down and hide should they ever be required. Obviously, there were constraints in that system. And so consequent to that, there was a lot of testing and development around what could a new system look like. And there were 2 systems that were tested and developed, a US Air Force system and a Navy system, which came together to create what we call Navstar GPS, or GPS as we know it. Not a major shift in terminology from NavSat, but a major shift in technology. And then we can start to run down this calendar quite quickly. The project first started in 73. First satellite was launched in 1978. Again, quite a massive achievement, given that the technology behind GPS was fundamentally different to the technology within the NavSat transit system. The Russians soon followed, and things started to develop. And roughly in that period, 1983, actually I do remember, because I was actually tasked with looking at GPS the moment the announcement was made around the availability of the system, consequently, due to the tragedy of the Korean airline was shot down, having strayed into Russian airspace. So in 1983, there was no real commercial receivers. There were a few technical receivers that were built into computers or had essentially processors that you could evaluate and start to create sort of an understanding of how the system worked. But actually, these receivers were very clunky. They could only really produce ranging information. A few of them could produce a position, but actually those positions were fairly slow. They were maybe every 10 seconds. Some added filtering, so you could get positions out more frequently. And so in those early days, we were actually quite challenged to start to use it. So we had to develop our own algorithms. We had to learn how to take this ranging information, these satellite orbits, this ephemeris information, as it's called, the orbit information, and compute positions. And again, I look at that and I look at how quickly we moved from, at that point, I was working for a company called Decker Survey, Rakel Decker Survey, who were very active in the positioning arena and created Decker Navigator, which was obviously one of the first radio navigation systems used on D-Day. But we could again go from 1983, starting to look at the system, to 1985, we were putting out our first commercial differential GPS service in the North Sea. And what drove that was oil. There was a lot of money, a huge amount of investment in oil exploration, and positioning was a real challenge. If you got more than 150, 200 miles offshore, there were real constraints on navigation capability. We had some low frequency navigation systems like LORAN that were able to give you 30 to 40 meter positioning, but actually nothing really able to provide the accuracy required for the first 3D survey operations. We talk about 3D as if it's a new thing now, but back in the mid-80s, we were working on 3D seismic, on building complex 3D models of the geology underneath the North Sea. And we required very accurate surface positioning to allow the 3D models, and these were coming from long streamers, 3-4 kilometer long streamers being dragged behind ships. And we needed very accurate positioning to control that framework to actually give us the ability to have accurate models of the subsurface geology, to look for the oil reservoirs, to look for the areas that we wanted to explore. So again, you can see an incredibly fast period of innovation, and that was actually driven mainly by the oil industry in the UK. So the UK was really a key innovator when it came to the application of GPS technology. The US were very focused on obviously the military application, but the UK was very focused on the commercial application. And that's a sort of serendipity thing with the North Sea exploding at the same time as the GPS first came available. Tragically, the following year, we had the Challenger disaster where the space shuttle exploded on takeoff. And at the time, we weren't really aware of the impact that would have on GPS, but it had a huge impact because the GPS satellites were built to be launched in the shuttle. And they weren't built to take the hard G-acceleration of a traditional rocket launch. Yes, the shuttles were launched obviously on a rocket, but within the cargo bays, they had an awful lot of capability to secure and control the environment. And launching on top of a rocket, which is where the satellites are normally placed when you launch, was a much different scenario. It's coincidental in 1986 when the Challenger disaster happened, I was actually undertaking one of the first commercial differential trials on a ferry. I had the pleasure of sitting on a British Sea Link ferry. For those of you who are old enough to remember, they were charming ships that ran between Calais and Dover. I had the pleasure of sitting on there for nearly 3 weeks. I did, I think, about 128 consecutive crossings of the English Channel without getting off, which I think probably still is a world record today. So that had a huge impact on new companies, small companies that had invested in building new commercial receivers because the program was going to be delayed. And in those mid-80s, there was really only about 8 or 9 satellites launched that you could reliably use, which meant that you were constrained to maybe 3 or 4 hours every 12 hours of viable navigation. And so we had to find ways to bridge the gap. GPS had given us a promise of so much, but actually, very sadly, that had been delayed. Another great acceleration happened in 1990 with the first Gulf War, where clearly the capabilities that GPS gave in the wide open areas of the desert and the desire to use precision munitions meant that GPS really came of age in that first Gulf War. But the American military hadn't actually provided at that point the military grade receivers. And so really the only receivers that were available at the time were a few, 1 or 2 commercial receivers. Right to the point that was declared, I actually moved to work for one of these companies in the US, a company called Trimble. And Trimble actually had a handheld commercial receiver that was very portable. And I'll come back to this. And actually that accelerated that company's fortune. It caused a few problems because suddenly there's a demand for hundreds of these, in fact, thousands of the receivers, because the military receivers weren't yet functional or available. So again, a lot of innovation in a very short period of time. And then things started to slow down a bit. Next generation satellites came along, improvements were made to the system, and GPS received full operational constellation performance in 1995, GLONASS similarly a little bit later in the year. Then selective availability was removed. This was a deliberate degradation of the GPS signal. And then things started to get exciting again. Europe decided it wanted to enter the fray, recognized the importance and value of global navigation satellite systems, and it did its first ever launch of a navigation payload, actually built from a technology company spun out of Surrey University, SSTL. And that was very much a very basic satellite that was really put up there to Bagsy the frequency spectrum. The International Frequency Organization sort of said, if you want to use frequency, you have to show that in space, you have to show that you have the ability to launch and support. So really, that was a glorified beach towel put up in space. The Chinese followed very quickly soon after with another system called Beidou, Compass more colloquially. And then really, as we move down, you can start to see the regional systems now coming into play. So again, in the last sort of 5 years of this last decade, a lot more capability through India, through Japan. And most recently, of course, one of the biggest issues in the GNSS arena has been obviously the UK losing access to Galileo, or at least the secure Galileo services. I'll expand on that in a second. And a proposed investment in a communications capability called OneWeb, which the British government is hoping that some navigation capability will be able to be abstracted from. I'm just going to move on now and just look at this. And hopefully this diagram I can explain. These are the orbits at which the various satellites, and this is a nice internet resource that's animated if you go onto Wikipedia. You can see obviously the Earth. And then very close to the Earth, hopefully you can see these 3 orbits, which effectively relate to Hubble, the International Space Station, but also Iridium is there, which is a global satellite communication system. And it's in these orbits that the OneWeb system is planned. And this, in fact, is the orbit height that the original NAVSAT transit system operated in. You have to go quite a long way out to 22 to 25,000 kilometers or 24,000 kilometers to get to the middle Earth orbits, the Galileo, GPS, GLONASS, Beidou solutions. And then even further out to get to the geostationary orbits, obviously, which is where mainly our satellite communications come from today in Inmarsat systems like this. And then obviously the graveyard orbits are put out even further, where effectively it's a parking orbit, and hopefully nobody will notice that stuff up there, at least for a few years to come. Now, actually, this shows quite interestingly some of the challenges that maybe the OneWeb system will have if it wants to provide a navigation service. The reason that GPS, Galileo, GLONASS, Beidou were put there is that they are reasonably stable orbits. You can model them. You can provide good orbital parameters. You can get a lot of satellites up there that have a good visibility, that maybe between 4 or 5 hours. One satellite at the highest zenith is visible for, the lower satellites obviously for less period. When you get down to the low Earth orbits, down at say 1,000 kilometers, you really are talking about satellites that whiz by, maybe in 20 minutes, as many of you might have noticed by watching the ISS. You can see how quickly it transits. You also have very high degrees of drag there, so it's very difficult to predict accurate orbits. And in fact, accurate orbits are critical to GPS because you need that not just for positioning accuracy, you need it for angular accuracy, for orientation. And also with these very low-cost satellites that go into those orbits, you have a limit to the technology you can put on board. The cost of a OneWeb satellite is about $900,000 US. The cost of a space-hardened atomic clock, which are critical to accurate ranging systems, cost about $2 million. So you can immediately begin to see a challenge when you're trying to force fit a very low-cost disposable satellite system with a lifespan of a few years with a very high-cost technology. Now, that doesn't mean to say that systems like OneWeb can't provide additional augmentation. They can, in the same way that EGNOS can provide a communication correction to GPS and also provide a ranging solution in their geostationary satellites. They could also provide some element of the old Doppler frequency that transit initiated of. And you can mix solutions, you can blend these in, And if you did have decent clock control on those satellites, and let's never say never for low-cost, high-performance clocks and software-controlled clocks, you could actually provide a framework that might augment GPS. But the question will be why, not whether. And the why is a big question, because these satellites operate at Ku band, which is a very different frequency from L band. They have different antennas, different processing capability. And if there's going to be 100, 120 satellites up there, why would you want to put in quite expensive componentry into something like a smartphone when you didn't need to? There might be some military applications where the jamming resistance or the stronger signal that comes from these low Earth orbit satellites might be useful. But there are clearly many unknowns around using these new technologies for satellite navigation. And whilst no doubt a lot of money will be spent on research, personally, I'm still challenged by the commercial motivation behind that decision for navigation, not obviously for communication. So just moving on, everybody will have seen a similar graphic to that, you know, with the current GPS or any of those constellations. You have a circular orbits, and like the polar orbits that the communications satellites like Iridium are in, or even Transit was in. These are circular orbits. You get good geometry. You're able to track. Most receivers can track pretty much up to all in view now, which could be at any one time 30 or 40 satellites. And obviously very sophisticated signal processing in those receivers. And just from the top down, you can see a lovely GPS satellite, actually one in one of the science museums in the States, or aviation museums, a Galileo satellite, obviously an artist version, and a GLONASS satellite. And just to get a view of scale, this is a GPS satellite being prepped for launch without the solar panels extended. So you can see they're not small. A CubeSat or a small satellite, the OneWeb or Iridium satellites, will probably be about the size of one of those panels down there in the bottom of that tall satellite. So again, you have a challenge there about how much technology you can build into these, and obviously how powerful the transmitters could be. As I say, they're optimized for communication, so they do have good communication antenna design, but navigation antenna design is a different thing. How accurate is GPS? And if there's any of my colleagues from on the survey, I'll probably recognize a diagram I've used before. I think it's the only one that I've kept with me. Here's a nice road project, and GPS in its standalone mode or global navigation. Many of you will get this from your smartphone, around 5 to 10 meters. But there are many versions of GPS, a correction applied to the GPS signal to take out any residual orbit errors, any residual ionospheric errors, the delay of the signal coming through the active charged part of the Earth's atmosphere. And you can even get down to a new technique that's achievable with the new generation satellites, both Galileo and GPS, that allows you with a single receiver to get down to around about 20 to 40 centimeters through an iterative convergent approach using multiple frequencies. And then for surveyors, and I now declare myself as a surveyor, we can get down to a few centimeters. In fact, we can actually get down to a few millimeters with very specific measurement techniques, but we can get down to a few centimeters for setting out surveys, for construction surveys. And I want to talk a little bit about how these systems have evolved by looking back rather than looking forward. The GPS signal is quite complex now, and I'm not going to spend too much time on this. I want to get to more fun shots of GPS in action. But you've effectively got in standard GPS 3 frequencies. It's frequency diverse. Within these frequencies, you have modulated codes using binary offset keying or binary phase shift keying. And effectively you have 3 primary codes on GPS. You have the course acquisition code, which is this powerful code here in blue. And that was really designed to allow these other code sequences to actually be found, because these are spread over much wider bandwidth, much more complex encryptions. They repeat over hundreds of days. This repeats over milliseconds. And so this was really a sort of a way of actually getting to this code with a handover. So you track this one, you would, by some sneaky techniques, piggyback onto this code, which was the military code, which is much more resistant to jamming and much more stable in a complex radio environment. By having it on 2 frequencies, you can build out good models for ionospheric correction. And actually, as the system has evolved, even more signals have been put on, more sophisticated encryption techniques, the M code, which the M code here is a new military code. Originally, the P code was the military code. And then the latest version of GPS has an additional frequency set. And this frequency diversity is really heaven to a digital processing chip, to a signal processing capability. You have the ability to blend it, play around with it, difference it, do all sorts of clever things. And it's that inherent structure, a mixture of complex code structures, but also phase information that allows us to produce a lot more from the GPS signal than was originally planned. If I go to Galileo, Galileo actually has even more frequencies. Galileo has 6 frequencies and actually has 4 services. An open service equivalent to the service that the GPS uses, high accuracy service, I talked a little bit earlier about this precise point positioning, and then the system that we've lost access to in the UK now by withdrawing from the European Union is what's called the public regulated service. And this is an encrypted service that has been designed to be resistant to jamming and is only available to authorized government bodies. Now, that's actually a huge loss, I'm afraid, because I've been involved in some of the work around what this signal could do. And this signal was going to solve a lot of the concerns around jamming, around spoofing. And obviously, a lot of that isn't in the public domain yet. But we have lost a pretty critical element to secure navigation for things that, you know, could be recognized as not just, you know, military applications, but also civilian applications in contested environments. And good examples of this is we were looking and evaluating the signal in a number of projects for providing very accurate rail positioning with the view that this could be used for both safer rail navigation and reducing reliance on existing infrastructure. So that's actually a huge loss, I'm afraid. We've effectively lost access to one of the most sophisticated signals in space that exists today. But Galileo does have a search and rescue system. We'll pick up distress beacon locations. And it also has some additional commercial layers that may come in the future with additional or authentication for high performance commercial systems. Galileo also brought us along quite a complex set of additional multiple modulation techniques. It's caused a little bit of a frisson of tension between the UK government and the US government, partly because there's some incompatibility between Galileo and GPS, and partly because of some behaviors around how patents operated. But ultimately those were resolved, and now all is harmonious again. I mean, it always was, it just obviously caused a little bit of a hiccup at the time, which I had the pleasure of getting involved with by just happenstance of being in Washington as it all blew up. So Galileo, and behind all this, we've got to think about what isn't good about GNSS. And these are really the 4 key error sources that we worry about today. The ionospheric disturbance is a substantial one, obviously with high levels of solar activity. There's a 13-year ionospheric cycle, which essentially ionospheric levels go up and down in a very systematic, periodic way. But those can cause problems with GPS performance. Now, the latest receiver designs, certainly the last 10 years, have really managed most of that. But a major solar flare, will have an impact on GPS, GNSS, but it will also have an impact on other satellite systems and, of course, on our communications networks. But actually, a lot of work has gone into this, and I'll talk a little about some of the early projects there in a minute. Another area that used to cause us more problems in the past was reflected signals or multipath. Again, these multiple frequencies, multiple code structures, software-enabled receivers, in fact, in some cases, software-only receivers, are able to handle multipath much more effectively. And in fact, the multipath signal is actually quite useful. You can actually detect the multipath signal back in space, and there has been some work to actually use GPS multipath as a sort of quasi radar and look inside buildings to see whether or not you can actually see reflections or shapes that might be a hidden object of interest, like a large aircraft, for example. But the two that worry people the most at the moment are jamming and spoofing. Jamming is essentially denial of the frequency that GPS operates, and spoofing is when you actually try to trick a receiver to track your signal, and therefore, and essentially it believes it's tracking a true GPS signal or GNSS signal, but actually you drive it in a location that you want to take it, i.e. make the system inaccurate. And over the last few years, there's been examples of quite deliberate jamming and spoofing activities, both in areas like the Black Sea. In fact, I was in Seoul a few years ago where there was a major jamming attempt that took out an aircraft one happened to be on that was meant to be landing at Seoul. But of course, there are redundant navigation systems on aircraft, so we landed safely. But these are two of the most significant issues today. Some of the frequency diversity in GPS, GNSS helps, but this is possibly one of the areas that OneWeb may be able to help, not to provide an alternative navigation solution, but be able to help detect when you are being spoofed by showing that the GPS signals are not telling you the truth. Again, there are simpler techniques that haven't really been adopted yet, primarily because people haven't seen this as a significant failure today. And in fact, one of your colleagues is listening today, Rick Manner's working in these areas on having antennas designed for effectively avoiding spoofing. And actually, even the simple thing of having two antennas at a known distance apart, you'll be able to determine whether you're being spoofed, because it's hard to spoof those two antennas because you don't actually know where the antennas are, and the antennas know that they should have a fixed distance between them. And the geometry of spoofing compared to those antennas will be different to the geometry of the satellites compared to those antennas. So a receiver should be able to detect quite quickly. This is an area I think that the solutions will come quite quickly. I think it needs one of those exogenic shocks to scare people. Even more than they are today, and possibly isn't a real concern for the sort of commercial sort of smartphone sort of GPS. Jamming is challenging, localized jamming probably more than wide area jamming, but actually I look at jamming as a problem regardless of whether or not you're jamming your GPS signal. It's probably as easy, if not easier, to jam your 3G or your 4G locally and take out the ability to report a position as it is to jam GPS. Either which way, augmentation is necessary. And when you're looking at applications that are moving towards safety critical, you know, there are already augmentations of a smart car, for example, will have a radar system, a LiDAR system, a video imaging system to actually provide navigation data on top of GPS. It will have map matching. So ultimately, when we look at the problems, we really need to take a sort of a more systematic approach and identify them by use case, and then identify what's the right solution. But overall, GNSS has been quite reliable, with a few hiccups, but those hiccups are few and far between. But it isn't an area we should be complacent about, and an area that I think we need to look at in a little bit more detail, and maybe have minimal operational performance standards legislated if you want to use GPS in an aircraft. Now, they are there already, but they're not as hard when it comes to things like spoofing resistance or jamming resistance. I'm going to do a little distraction now and pull back to the title of the talk, because I think there's a few interesting things around GNSS and GPS. GPS actually started with a key number of individuals in the States, one of whom, Brad Parkinson, actually I used to work for. And he was very involved with designing the concept of GPS at the system level and the relativity effects. And Einstein has a significant impact, Einstein's theories have a significant impact on GPS. And in fact, GPS was really, and this isn't me stating this, it's Mr. Parkinson, really, Professor Parkinson, is really one of the first proof positives that Einsteinian relativity laws were real and had an impact. And that is, when is the speed of light not the speed of light? Well, of course, it remains the speed of light, but you might need to fiddle it. And the science bit, I think, is fascinating here, because general relativity predicts that clocks in a stronger gravitational order will tick at a slower rate than the observer if they are in a if the observer is and the clock are in a separate part of the gravitational field. Whereas special relativity says that moving clocks will appear to tick slower than non-moving ones. And of course, GPS and Galileo and GLONASS are driven by having atomic clocks on board. GPS generally goes originally for rubidium and cesium clocks, and more recently hydrogen maser. Galileo is a hydrogen maser clock with rubidium spares, and those are obviously very accurate clocks, able to provide timing, you know, at a few nanoseconds. But putting them in space and orbiting them means that there's some degradation to clock performance. Remarkably, and I've said one for QAnon on here, and it is remarkable and weird that these two effects actually cancel each other for clocks located on sea level anywhere on the Earth. So coincidentally, sea level, you don't actually, and you can't see the difference between special and general relativity, partly because obviously, well, the observer wouldn't see it in the same place, but the two actually cancel each other out. The impact of general and the impact of special actually cancel each other out. And that is weird, but is evidenced. So how did we get around this? Well, in the early days, they had to recognize that they couldn't change the speed of light. So what they actually did was they actually adjust the frequency standard on the satellites. So nominally GPS operates at 10 megahertz, the frequency standard, which is the core oscillator. But actually the clocks are tweaked up to that very long number there in megahertz, very precisely, to actually mean that the effective performance of GPS stays true to Einstein's theories. And people might say, well, surely people knew this before. And of course, they'd had indirect measurement before, but nobody had put up atomic clocks in space before because of the obviously physical challenge, the engineering challenges. And here was a real working practice example of Einsteinian theory. But actually, this also added other problems. You have very precise clocks in space, and hydrogen maser clock accurate to 1 second in a million years. You actually need very accurate coordinate systems. And surveying is really just distances and angles. And ultimately, as we know from the pyramids, set out with distances and angles. In fact, it's only in the last few years that people have stopped using pegs and wooden stakes to measure distances and angles or distances on road construction projects. The very same technique that was used in building the pyramids. But since then, we've recognized that to get very precise positioning, you don't just need very precise clocks, you need very precise orientation. You need a coordinates reference framework, which allows you to fix all of these complex moving satellites into a frame that allows the measurements to be translated to coordinates. And GPS orbits fundamentally drive one of the most important precision parameters in GPS. And this is why one of the challenges about low Earth orbits is how accurate can you predict those orbits. And we achieved that, or the designers achieved that, and had a small part to play in this. The designers achieved that by creating what's called the International Celestial Reference Framework, which was completed in 1995. And they did this by measuring to over 295 extragalactic bodies, mainly quasars. So GPS in your smartphone is directly related to a quasar at the edge of the known universe that ceased to exist about 4 billion years ago. And so in your hand is a device that navigates based on assumptions around the earliest elements of our universe and the assumption that we have an expanding universe. And of course, orientation is critical to this, and it's still a key challenge for reference frameworks. And any surveyor, and hopefully there'll be some of my colleagues listening, will know that setting out baselines to get good angular control on a project, and some of them I know worked on the cross-channel link, the tunnel, and getting good angular representation between two countries was always really challenging. You could get it good within your own country, but within two countries was difficult. And we did this in the early days by tying in what are called very long baseline interferometry stations, essentially radio telescopes that can pick up these signals. And I had the pleasure of visiting these three, Hartz-Bestuk in RSA, Hobart in Tasmania, and Alesund in northern Norway. And you can see here a GPS antenna in the snow over here. And here's a GPS antenna with a choke ring to stop multipath on the ground, close to the ground. That's actually quite a good place for a high performance antenna, because you don't get much multipath off the ground, assuming it's not covered in metal, and you don't have to deal with the wobble of the pole. And so we tied in all these stations around the world by taking very long baseline measurements using GPS, and they then projected those up to the quasars at the edge of the known universe. And there we get the coordinate reference frame, which gives us the ability to have very accurate positioning. Now, how do we use this? So here's a great example. It's been a few years around now. This is, again, wow, 20 years old. And this is where GPS was first used in this very high performance mode with these sort of very high accurate coordinate reference frames to actually determine that parts of the UK went up and down quite frequently. I'll explain this. If you look down to Cornwall, you can see these contours moving through with things like -50 and the orange ones coming through with 40. What that is the vertical displacement of that part of the country every day. And so it's going up and down by about 40 millimeters. So overall about 10 centimeters every day. And that's because of the weight of the ocean coming in, and also a little bit with high pressure increases the weight of the ocean pressing down on the crust. So essentially Cornwall is going up and down by around about this amount every day, which probably accounts for a few drunken walks early in the morning. But ultimately, GPS was really one of the first systems that allowed us to measure that accurately. And continental drift, UK is moving towards Norway, and GPS is critical for earthquakes. Now I'm going to finish very quickly with a few personal sort of selections of projects I enjoyed, interesting and quixotic, some of them. In the top left, you can see a very big dozer, D11. I worked with Caterpillar for about 5 years on how you automated this construction equipment. And I'm very proud that the antenna you see there and the bulldozer blade, the stick sticking up, there's actually two of those. This was one of my personal initiatives in innovations with a small team in California. And this allowed us to orientate the blade of the dozer by using GPS as a very precise orientation system. And this is building a highway in Saudi Arabia. This was 98, I think, 97, 98. The company we're working for was a Saudi construction company called Bin Laden Construction, which was actually Bin Laden, the father, had this massive construction company, building a highway project to Mecca across the empty quarter. Very hot, very difficult, very dusty. But one of the first real big users of machine control. They bought 12 of those dozers. They cost just over £1 million each, a D11. So a very big project, one of the first real major projects on live construction. So where the GPS was used to control the design and to realize the surface that they wanted to build. And it's also cool in that cab. It's also cool driving a big dozer, I have to say. The middle top one there was fascinating. This is a more advanced version of a system that we originally put out post Chernobyl. When Chernobyl happened, and this was a long time ago, 80s, wasn't it? A lot of contamination happened in Wales and in Scotland, Wales especially, where the sheep over a period of time would actually eat the sphagnum moss, would get contaminants, and therefore the meat wouldn't be safe. And to a certain degree, even the wool. And it's only in the last few years that they've stopped to have testing for this. So we had the cool idea of building a jacket for the sheep, for the lead sheep, there's a lead sheep, and tracking them. And then if they got a high degree of contamination, we could try to pinpoint where they had fed, where they had eaten. And those things have now become routine. They're now installed on elephants. They've now installed on, but actually the first tracking system we put on an animal was back in the gosh, I can't remember when Chernobyl was now, with a big jacket, but again, driven by a very specific problem. There's my wonderful Sea Link ferry. Sadly, I was on board that when the Challenger shuttle exploded. So that sort of dates that. Here's one of the first live construction projects. This is the Horizon Bridge, the Sunlink. And there we used survey grade GPS on the cranes and on the barges for positioning the caissons, which are the concrete structures that you load down at the seabed. So the first real interactive system, software based, using GNSS at the centimeter level. And that came from a very talented software team in New Zealand, who'd also developed a lot of the software for earthquake monitoring, and ironically, obviously where they were working and developed was Christchurch. So interesting synergies there. Here's the Guildhall in London. This is exciting to me because this is the first time we used a piling system, automated piling system, that I was involved with. And there that was being used in the reconstruction of the courtyard area. There were some Roman mosaics underneath that, and we put it on the continuous flow augers for the piling to stabilize the surfaces. And the great pleasure of a minister seeing this system and getting on what was a very muddy job site at the time, and getting onto the excavator, not realizing that when excavators slewed, that the cabs and the tracks didn't align anymore, stepped back in his nice suit and fell right down into a pile of mud, which was obviously very sad. GPS control here used for the CERN, again, massive construction project, needed very accurate control. To get accurate subsurface control, you need accurate surface control. And in fact, the cross-channel tunnel was one of the first projects to ever bring GPS together with underground tunneling to actually provide that. Subsequently used on obviously major projects like the London Ring Main, used on things like Jubilee, and obviously on CERN. Here's some very early gratuitous receiver shots. That's on the left, one of the first ever receivers produced by a company that were one of the innovators in GPS called Trimble, who I had the pleasure of working for 11 years. This was actually prior to GPS. This was their pre-GPS receiver called Luan. It's used a low frequency system, and they integrated GPS into that to actually build through the gaps in GPS performance and the gaps in the satellite. So this moved Trimble more into marine navigation before they could get back into survey. This one here I'm holding up in the sun of summer, last summer, is a civilian version of the military receiver that was used in the first Gulf War. As you can see, very portable, a bit heavy still. You wouldn't want to hold that one-handed for too long. The big difference between this and the military version was the military version was green and had a military grid, but apart from that, not a huge amount of difference. And over on the right is the actual military version at the same time, if they had been available, quite a big man-pack version. So you can see why this receiver was very attractive in the Gulf War. We sold, well, probably thousands of these at very short notice. And in fact, we had a lot of people trying to buy them, coming to offices at the time, who were being sent out to the Gulf, and actually had to go out. Actually, we also sold some survey equipment to 42 Survey Regiment, and they were doing the survey control in advance of the tanks. It's funny to think that people think that it's the frontline troops that go first, but actually in the Gulf War, the surveyors went first. They needed to set up precise control. So when the tanks came through, the tanks had something that they could position and recalibrate the inertial systems on, because obviously tanks need accurate guns that can fire when moving. And if you have a huge empty space like the desert, you don't have the control, and the tanks didn't actually have GPS. So we sent the surveyors in front. I had the pleasure of being in Bahrain training them when the Scuds were flying, which was one just landed about 2 kilometers away, which was a bit spooky. And here's some just personal stuff here to apologize, a bit self-indulgent. This is the first ever rig move in the North Sea that was done in 1985. Yeah. You can see the people looking a bit nervous. 2 reasons. One is we had to climb those legs, the jack-up. It's a jack-up leg to put our GPS antennas and our navigation antennas up. I froze on the leg and had to be talked down by Jim, who was a very bluff Yorkshireman. He told me no uncertain terms that I had to get down quickly. But the other thing was a bit scary. You actually got lifted onto these on a basket. You had to leap onto the basket, hold on, and the crane pulled you up and dragged you over. But this is the sort of equipment we took on board. And as you can see, fairly heavy equipment, old HP 9826 computer there. We didn't have software interfaces, or we used to have hardware interfaces, and some other navigation equipment and a sat-nav receiver, the old transit receiver. And so quite a lot of navigation equipment to do a job that people now expect to be able to do with a single device, a smartphone. Another exciting project in China in '86 is the first time that we took a GPS receiver legally into China. A lot of fuss. I was based in Shanghai, and it took about, the equipment disappeared for about 3 weeks. I had the pleasure of living in this beautiful Sussex looking house in Shanghai. When the equipment eventually arrived, it was missing a few screws. This is a Trimble 4000 GPS receiver. At this time, the receivers couldn't do differential calculation. So I helped, and a colleague and I had written software on a BBC Micro, in fact, to do the calculations. And we used to pass out the corrections, believe it or not, by voice. The signals, error signals were moving so slowly. Now we take all this for granted. This is again, self-indulgent. This is a picture of where I lived up country for about 3 or 4 months. Beautiful accommodation. Behind here, there's actually a stone cairn with a dead donkey in it, but that's a story for another time. And then a base up in northern China, where I had to live for quite a few months, less appealing. But again, first time GPS was used in China, and consequently, you know, China has become a major player in the GNSS industry. Great thing about going to China in the 80s is that nobody else was allowed there. It was still a closed country. And in fact, the Chinese were only just being allowed to travel themselves. So very rarely did I ever see anybody. As you can see here with some shots of the Great Wall of China and the Forbidden Palace, nobody there. I'm sure that's not the case now. I had planned to go back to China this year or last year, but obviously didn't. A similar survey work in Australia. I wasn't as tidy as perhaps I am now, and used to live in tents for months at a time. This is an old TI 4100, which is one of the early most expensive receivers, but had the capability to track on the P code, but also required you to download orbits later. I do apologize to my surveyor colleagues. That's not a very well installed antenna. I used to criticize and complain when I saw my colleagues doing that, but I am just as guilty, I suppose. A few interesting shots from other places. This is a survey grade receiver, the first one that ever came out. This is able to survey to a few centimeters. This was Guinea. This was obviously Nepal. I actually didn't take that shot. A colleague of mine, Paul, did. I was on the ground base station. He had to get up higher into the mountain. This is the first time we tried to do a resurvey of Everest, not by physically going to the surface, but by reoccupying the baselines that we really used to survey Everest, the surface of the height to top of Everest. And we found those original baselines to be accurate to a few centimeters, which, given they were measured over tens of kilometers, was phenomenal, actually. One of the longest baseline, I think, was 42 kilometers, and they were with accuracy. And this is back in, obviously, when Everest was around, so Survey of India time, so incredible surveying work back then. Precision farming we take for granted. Here's a set of precision farming trials we did in the mid-90s, I think 97. First season ever for a commercial precision farming system. I had the pleasure of going up from the south of France to the north of England with this case system. You can see how sophisticated this system is, even back, 20 plus years ago, 25 years ago. And we make assumptions today that things like precision farming are new. They're not. They've been going along for a long, long time. What has changed is the affordability of the system, not necessarily the capabilities. This is measuring the yield. It's measuring the moisture content in the grain. It's using satellite delivered corrections with the antenna up here. Very sophisticated systems. And probably my favorite project of all was the opportunity to fly to the North Pole with the first ever commercial survey grade receiver. to actually see whether GPS could work very high altitudes to very high accuracies, centimeter level accuracies. The plane we flew in was older than me. It's an old Comet, for those of you that recognize this. It's flown by the RAF. It's called Canopus. It was used as a test plane. Unfortunately, it was retired a few years ago because of the cost of maintaining it. But what we did in this project, which was interesting, is there was quite a lot of, we chose, it was flew when there's a period of ionospheric storms, actually. So we set up on base station, or survey quality base station, in Thule in northern Greenland. There's a nice little map. It was like a map of where the top of the world club is, actually, where you can have your cocktail. And then we flew to the North Pole, flew around it a few times and flew back. What I did before we did that is set up a very precise ground control framework and then effectively let the system run. So we flew there, we flew back. Many long distance, obviously, as you'll know from looking at the map. We managed to land and control the reference coordinate for that plane to around about 10 centimeters, or better, actually. And we did that by surveying outwards on the aircraft and surveying back and closing the survey. That's not great survey practice, but you can do it both ways. You can go forward and you can come back in post-processing. And both those two tracks agreed to around about 5 to 6 centimeters. Using survey grade equipment in a high ionospheric area. So that began to prove to us that you could really drive GPS performance. And that's why I think it's a disappointment that we've lost some of this new access to Galileo, because ultimately the signal capability that's embedded in the PRS code is phenomenal and would allow us to do so many things. We can do a lot with the open signals, but we could do a lot more with those controlled signals. And then finally, I'll probably run over time. Thank you to Professor Einstein. My favorite quote from him is, logic will get you from A to B, navigators, but imagination will take you everywhere. And I think GPS and GNS is a story of imagination. It was originally designed for military use, and now we use it in every part of our life, from our smartphones to our Deliveroo apps to, you know, in-car systems, you name it. And genuinely, it's I think, a hugely important technology with so much more still to come. But like all technology, you can still get lost. And if you don't have a good map, as the little sign will show you there, if your map's not up to date, your navigation might not be either. So anyway, that's me finished. Thank you very